Now recall that the use of Lagrange's method is a very simple but not particularly efficient way to accomplish interpolation to data points. So at the end of the previous lecture I mentioned a better approach is to use what is formerly known as Newton's method. Newton's method is a different way of constructing and interpolating polynomial, again with the assumption that the data is accurate and the data points are unique. We'd like to construct an interpolating polynomial that will fit the data. The form of the Newton polynomial, or the Newton's method, generates the interpolating polynomial of the form that you see here in this slide. You'll notice that each of the a's are scalars, and the x coordinates are indicated as x0, x1, up through xn minus 1, as we've seen before. So again, the data points that we are interpolating to are of the form xi, comma yi, I indexing from 0 up through n minus 1. And so the polynomial has this form. You'll notice that you'll start off with a scalar a0 plus x times x minus 0 times a1, and then you'll have all these monomial product terms. All the way through the very last product term will involve all of the x coordinates, each one of them subtracted from x, and that'll be multiplied by an. So for the case of 4 data points, so you have data of the form xi, comma yi, order pairs, where I is indexing from 0 to 3, so that would give you actually 4 ordered pairs. That would generate a cubic polynomial by Newton's method, and it would have this particular form. Noticing that we have factored out the x minus x0 term from the previous terms, and then we would factor x minus x1 from the last term. So if you look at this very carefully, this particular polynomial can be constructed fairly efficiently, which you'll notice that if you work from the inside back outward, what you've got is you would take a scalar value here, a3, multiply it times x minus x2 if you were evaluating this polynomial at a particular x. So if you wanted p3 of the value 2, you would put 2 here and then subtract whatever the second x coordinate, the third x coordinate was. You could see that what you'll end up doing is making a subtraction, then a multiply, and then you'll add a value, and then another subtraction, multiplication, and add. So it's sort of an interesting sequence of operations to unravel the original evaluation of p3 of x. So it turns out if you can take this particular form the way we've written it, and is indicated in the next slide, actually write it as a recurrence relation. What do we mean by that? If you initially defined the first polynomial as p0 of x as, say, an, you could generate all the polynomials of the form pk of x from k from 1 to n by taking a scalar and then adding this monomial term x minus xn minus k times the previous polynomial. So it shows you a way of, say, taking p0 of x and then getting p1 of x from p0, and then getting, say, p2 of x from p1, and then so forth, so that you can build up all of the polynomials that you need, taking into account a new data point as you go through it. So it's a very, very clever way to use recurrence to build up the Newton polynomial. So you take lower order polynomials of the Newton form and generate the higher ones. The Python implementation is very straightforward and actually looks very much like the recurrence relationship you're seeing up there. And we're just using array structures and the range function to iterate, to generate the list appropriately for the iterator variable k to index through it. So, so again, just playing a little bit with recursion here, what we're saying is that you would get p1 of x as a n minus 1 plus x minus x n minus 1 times p0 of x. So that would be a way of how you could take, this should be minus there. That's how you, given p0 of x is equal to, say, this an value, how you can generate, using all the ANs, all those scalar values, how you would generate the next polynomial. So forth, just again one more time, you could get P2 of x from what? A, and just using the formula n minus 2 plus another multiplication of a monomial term x times x n minus 2 times P1 of x. So shows you again how you build up the family of these polynomials. So let's make sure that we understand that this polynomial will interpolate the data, and if that is the case, and you can show that it would, then this has to hold, just like it did for Lagrange's, that when you plug in xi into the Newton polynomial of degree n, you should get yi for all of those n plus 1 data points. Again, this is simply the definition of what it means to interpolate the data. You plug in the x, you get the y back. It fits that data. So if you were to then write out the equations for all the polynomials, as we've indicated before, then given this constraint, then when you plug in, for the first case, we'll assume that, when you plug in Pn of x0, you get y0 back, and that polynomial is just a scalar value, right? Then these are all the other polynomials evaluated at the corresponding x1s and x2s and x3s all the way up through xn's. So these are the equations that match this constraint, all right? Given that the polynomial is defined, as we had earlier, as simply these terms of x minus x, well, let's just go back and just so we're not confused. The polynomial is defined as we had in the original slide, and you just have as many terms as you have data points available, okay, to interpolate. So if we go back now to our constraint, again, these are the equations that represent the interpolation of data points as we move through them. This is the initialization, that y0 would have to be equal to a0, but then when you take into account x1, again, we have to have that we have to have that Pn of x1 is equal to y1. It has to interpolate that data. So our Pn of x1, though, will have this particular form, right? And the next equation here is a reflection of Pn of x2 is equal to y2. Again, our polynomial has to fit that data point. But the polynomial at that point would have this particular form. Okay? This is a representation of Pn of x2. Okay? And then finally, this last equation represents the interpolation at the very last set of order pairs, that Pn of xn equals yn. Okay? All right. So you'll see that the polynomial has a more, when you're interpolating the final data, it has the most complicated form. But the polynomial is very simple when you're only looking at 2 points, when you've only seen 2 data points or 3 data points, so forth. So it gets more complicated because it's the recurrence relation. Again, as you build up the polynomial as you process more of the data. Okay. Again, if you go back to the previous code that we were seeing, you can see this process. Again, that the polynomial starts off very simple and you keep building them one by one as you go through it until you have the final polynomial. Okay. All right. So, and again, well, I should have corrected this. The n here, yeah, we're building, depending upon the degree of the polynomial. Typically, again, you have n plus 1 data points and you're generating a polynomial of degree n. Okay. So, what we'd like to do next is find a shortcut that would allow us to determine what the a sub i's have to be. So we have these constraints. If we go back to the previous slide, we've got these constraints. These equations have to hold for our Newton polynomial to fit the data. Okay? So if they have to hold, the question is like, all right, well, maybe what we've got here is like some kind of a linear system where I know the y's and I know the x's, and I've got to figure out what the a's are. So you could possibly rewrite this as a linear system, but it turns out there's a much more efficient way to generate those a sub i's, and it's what's called, and the way to do that is using what's called the Newton divided differences. And the Newton divided differences are just different subtractions or differences between the y coordinates and the x coordinates. So the notation is indicated here for what a divided difference is going to be. The very first one you see is called the first Newton divided difference. Okay, this is the nabla, or sort of an upside down delta symbol there. And you don't put for the first order difference, you don't put a 1 there. You just write the symbol itself, and then represent the divided difference for y sub I will be y sub I minus y0 over the difference of xi minus x0 for all of the i's from 1 to n. The next representation is called the second order divided difference. Notice the 2 there sort of as the superscript on the yi. It involves the differences of the previous first order difference, all right, with the difference involving y1. So these are formulas that basically represent different differences that we'll see graphically in a minute how they are related. But notice that the i's are changing, so that the number of differences that you're going to compute starts telescoping till you're down here to the very last, or what's called the nth Newton divided difference, and it involves just a simple difference of the n minus first order values over xi minus xn minus 1. Okay, so don't worry about the complexities. You don't have to memorize this. It's just a very general way that Newton polynomials can be generated, and you'll see in the next slide how we can use these divided differences. They're easy to program, and how you can use them to determine what the a sub i's are. Because again, if we go back to the previous slide that we had earlier, you have the x's, the x coordinates. Once you have those a's, the polynomial is fully determined. Again, the polynomial here, you don't see any of the y coordinates. It's all based on the x coordinates and these mysterious coefficients, the a's. So what we're trying to do is find a way to determine what they are, given the fact that when you plug in xi into this formula, you have to get back yi, okay, because it has to interpolate the data. It's mostly just algebra, trying to figure out clever ways of exploiting that. So this is a Python code that will actually generate the a sub i's. It will compute the divided differences for you. I'm going to show you sort of a pictorial way of doing that before we get to this, before we understand what this code is really doing. So what I'm going to do is I'm going to go back to this definition here. I'm going to show you how these divided differences we built up for maybe 5 data points. Okay, so what we're going to do is we're going to represent, what we're going to show is that using the divided differences, as you see there on the screen, we can actually show, I'll write it over here, we can actually show that first of all, a0, that first scalar in the Newton polynomial form, will be the first y coordinate of your data. The a1 coefficient will turn out to be this first order divided difference on y1. a2 will be the second divided difference on y2, using this notation divided difference on. And this pattern will continue all the way through the nth coefficient, and you can probably guess what the form is. It'll be the nth divided difference on y sub n. So these are just a continuation of the process. So this is how you can generate all the coefficients for the Newton polynomial using these divided differences. So let me show you the tabular form that you can use to produce them, which will help explain how the Python code is defined. So what we'll do is we'll look at the case where we have, let's say, data points, 5 of them, x0, y0 through, let's go ahead and write that. So let's suppose we have the data x0, y0, x1, y1, and this continues all the way up through, let's say, x4, oops, there's that selection problem again, x4, y4. So we have 5 ordered pairs there, or 5 data points. And what I'm doing then is constructing the 4th order Newton polynomial. Again, if there's 5 data points, the interpolating polynomial will be of degree 1 less than the number of data points. So we're looking to construct P4 of x. So that's what we're trying to construct, P4 of x. So how we're going to do that is we're going to represent this in a tabular form. We'll represent it, I'll try to fit it in here, and if I run out of room I'll clean it up. So let's just write down each one of the x-coordinates of the data that we have in a column here. So I have a column written with all of the x-coordinates of our data. And then next to that, let's write down the y-coordinates that we have that match them. Again, this is the data that we're interpolating. The polynomial has to go through all of those ordered pairs. And let's just, again, indicate with a line that we have all our data in a column or format that. So if we're looking at divided differences involving the y-coordinates, and that's what the divided different formulas, as you have on the previous slide, involve the y-coordinates and the x-coordinates. Once you have these first 2 data points, the x1, the x0, y0, the x1 and y1, you can compute the first divided difference on y1. Okay. How do we know that? Let's just quickly go back to the previous form. So here's the formula here. If the I was equal to a 1, you would need y1, y0, x1, and x0. See how that works? So it's just using that formula. So we can immediately get the first order divided difference on 1. Similarly, as you read the next data point, you would be able to get the first order divided difference for y2, and so forth, the divided difference for y3, and then the divided difference for y4. As you read more data, you can compute the first order differences. And this process continues. Once you have the first 2 first order differences, you would be able to produce the second order difference for y2, the second divided difference for y3, and the second divided difference for y4. And you can see the pattern. It's telescoping, and so when you have these 2 divided differences, you could get the third order divided difference involving y3, and then the third order difference for y4, and at the very end you would have the 4th order divided difference on y4. Okay? And what's really, really nice if you go down the diagonal here, just tracing my pen here, if I went down the diagonal from y0 to the first order difference in y1, to the second order difference in y2, the third order divided difference for y3, and the fourth order difference y4, what are those? Those are those coefficients that we were trying to seek. Again, if you go back to the previous slide, we've just generated what the AIs have to be on that diagonal. Okay, so this is a very efficient way to take your data points and generate those AIs, and that's exactly what the Python code, very simply put, is doing, where it uses the x coordinates stored in the array called x data, and you have to initialize starts off as the A array will start off as a copy of the y coordinates. That is to say, this y data is nothing but this column right there, right? And we're just doing the proper subtractions with the A array here, and then updating as we go through to produce the appropriate diagonal. Right? So it's a clever way of saving storage, using A to represent, initially setting it to be the y coordinates, and then as we go through, we are updating it with the appropriate divided differences as we go through, so that at the very end, what I really have left in the array is each of those diagonal elements. Now the book actually shows you a complete code, and we're going to look at that next, so that you could see what the Newton interpolating polynomial code looks like, because you'll be using that. It's a very, very nice routine to be able to use anytime you need to interpolate data. So here what I'm showing is the Newton polynomial Python code that's available on page 108 of your textbook. The module is called Newton Poly, and I will provide newtonpoly.py for you on Blackboard, so it'll be available to you. And the doc string pretty much indicates that this is a way of evaluating Newton's polynomial, say p at a particular value x, and that the coefficient vector ai that it needs can be computed by the function as indicated right here called it's a shorthand notation for coefficients. So so there's a function coefficients that takes in your data points, x data, y data, produces the coefficients that is then used by this function called eval poly to evaluate the polynomial. So it's actually, you construct the Newton polynomial coefficients first, so you know how the Newton polynomial can be evaluated, and then you would actually evaluate it at some particular point, x, okay, given x data and the coefficients. Because if you go back to the definition of the polynomial, remember, the definition of the polynomial just had x minus xi terms multiplied by those a's. That fully determined the Newton polynomial, and that's why those are the parameters. This x right here that you see right here is just say, take the polynomial that we construct with the first two parameters, the array a and the array x data, and evaluate it at, say, some point like 2, 2.5, 1,000, whatever. Okay. But you should be evaluating it most likely within the interval that the data lives, so that if not, you're using it as a prediction that if this x is not within the interval of the values of your x coordinates, then maybe you're trying to do a prediction. All right, so if you look carefully at the eval poly, you can determine the length of the degree of the polynomial by knowing how much data you have and then subtracting 1. Remember, because if you have n plus 1 data points, then you would have a unique interpolating polynomial of degree n. So that's why that's a -1. And then this is just the code we had earlier for recursively generating the polynomial once we know what the coefficients are. So here's the coefficients function that will actually produce the coefficients using the divided differences formula. And it's got a little bit different form than we had than I showed you earlier, using slices of the array. M here is just the length of the X data, the number of data points. But it's a very nice compact way of generating the coefficients, those diagonals of the divided difference table. Now I'm going to show you an illustration of using the Newton-Poly Python script to do an interpolation. The example I'd like to highlight is example 3.4 on pages 114 and 115. I have a Python implementation of this example, and I will provide that with the Newton-Poly.py script on Blackboard. So again, I encourage you to take these examples and run and test them on your computer, just so that you can get a sense of how to call these routines, because then when you do your other homework, you'll have some examples that you know work. So what this problem is, given this particular data in this table here, it turns out the data actually comes from a particular known function, and the function is this f of x equals 4.8 times cosine pi x over 20. So this is actual data that if you plug in x.15 into f here, this is what would come out. Okay, so what we're going to do is we want to generate a Newton interpolated polynomial. There's 1, 2, 3, 4, 5, 6 data points. So if we have 6 data points, and if I asked you for the 6 data points, what's the degree of the unique Newton interpolating polynomial? I'd hope you would say that you would be generating a 5th order polynomial, P5 of x. Okay, and so what we're going to do is we're going to take the data and generate the Newton interpolating polynomial here, and then go through and evaluate the polynomial against the true function f, just to see. We know it will match on these particular points, but how does it match in terms of, you know, all possible values of x or y within a certain range of values? Okay, because again, the idea is that when we're interpolating, you know, to the data at certain points. You know, we're trying to get a fit of the polynomial through the data, but you know, there could be some errors here, because you know, it's possible that the actual function, you know, that goes through this data has you know, maybe a particularly different type of form. I can't get this to work right, but you know, maybe the data you know, the function might go through the data in a different form, wiggle through this perhaps, and there's going to be some errors. So there might be, you know, I can't seem to get it to work here with the selection, but we're trying to see the difference between what the polynomial looks like and what it's doing in between these interpolated values versus what the real function's doing. Okay. Tried to draw this again. So what I'm trying to say is that if these are the data points on our Cartesian coordinate system, that in this smooth curve right here is the function f, the Newton polynomial will go through those data points too, but it might be wiggling like this, you see. And so what we're kind of interested in is seeing how well it fits the data, not at the points we're interpolating, because we know it fits that. You know, how far off is it? How big are these little error bubbles that we're seeing? That's the issue we're trying to see. How well does the interpolating polynomial? Because polynomials do wiggle, and we have to be careful sometimes about what those errors, how big those errors can be. So here is on pages 114 and 115, here is the problem. Again, I will provide this code to you on Blackboard, but again, the idea is to take that data and build the fifth degree Newton polynomial that will interpolate to it, and then let's see how well it fits the more general range of data. And we're going to interpolate it at these points and then evaluate the polynomial at increments of 0.5, 1, 1.5, and so forth, all the way to 8. So again, let me explain what we're doing. We are taking these data points to build the polynomial, and then we're going to go back and plug in arbitrary values of x and see what the value of the polynomial is at those values of x versus the function itself. I want to see how well it fits it. And again, we know that it perfectly, there is no error at these points, at x of 0.15, 2.3, 3.15, and so forth. We know there's not going to be a there because that's what it means to interpolate. So you can see in the Python code below, using NumPy, declare an array with a list for the x coordinates. The other array, y data, will be created from a list of the y coordinates. We call the coefficients functions that's provided. You need to use the from statement to import the Newton poly, all the functions from the Newton poly module. And we're going to print a table. We're going to print an x value, what the interpolating polynomial would give you, as well as what the exact value is. Okay. So let's just continue on. Again, you're printing a table out, and then just a very simple loop. We're going to loop over these arbitrary values of x, because again, we've already built the Newton polynomial by the coefficient function, because all the eval poly function needs is those a coefficients, our x coordinates, and then where do you want to evaluate it at. Okay. So again, here the x is going to range over from 0 up to, but not including, 8.1 in increments of 0.5. Again, using the arange function. Each time we can tell you exactly what the exact value of the function should be, because we know what the form is. Notice we're using the cosine function from the math library, so we can specify it as math.cosine. We're using the built-in representation of pi as pi from math. So again, that's the exact function. There's a format so that we can print out x, the interpolated value for y, and the exact y. So each time I put in an x, I'm getting what p5 of x is going to be. Okay, and that's going to be stored in y. And when you run the code, this is what you would get. I'll show you the script in just a second, just so that we can see it run live. But I'm just trying to explain to you how the table works. Again, we loop over from 0 all the way to 8 in increments of 0.5. I evaluate the Newton polynomial at that point, and you can see that there are some slight errors, but it's fairly close for many of the values. We can get at least 2, 3, sometimes 4, sometimes 5. Notice this one's a perfect match, 3.5. Well, if we went back to the previous page and went back to our table of data points, you remember 2.3, 3.15, 4.85, those are the data interpolated to. Sometimes you'll notice that data points near them, the accuracy is pretty doggone good. So it's just the question of, maybe when you get farther away from the actual data, some of the errors will creep in. But for the most part, this interpolation is very, very good. Again, we're building an interpolant without even really knowing where this data came from. The data actually comes from a real function, and we used a Newton interpolating polynomial to fit it, and the interpolating polynomial is mimicking what this cosine function really does. So it's a very, very powerful technique. Sometimes there can be errors, but for this particular case, the degree of the polynomial isn't too high. If you get higher order polynomials, with using 10, 15, 20 data points, the errors could be a little bit more severe. Here's an illustration of the example 3_4.py file that I'm going to post on Black for you to use. Again, this is pretty much exactly what we just saw in the textbook. You're welcome to take it, play with it. You could actually change the values here to see how the interpolating polynomial would do if we push the values even farther out. And maybe that's something we can do right here. Let's go way farther beyond 8, given the fact that the x data goes as far as out as 7.95. 8.0 is close to the 7.95. Let's really push it past up to 10. And I've also changed the increments here of 0.25. So maybe we'll want to see a little bit more data points to see the difference between the interpolating polynomial and this cosine function. So I'll go ahead and just run the code. We're going to get a lot of output because I'm using a finer mesh. In other words, I'm looking at every quarter, 1/4 point between the integers. So when we run the code, you can see the outputs here, and notice again that what I'm doing is in the book they only had like 7. You saw the interpolation. You saw the interpolating polynomial at 7, as well as the exact function at 7, and then 7.5. I've added another point, 7.25, although I didn't print the 5 next to the 2, and 8.25 and 9.25. But also notice something. When you go back to the array and look at the data points that we used to fit the Newton polynomial, remember it went up to 7.95, and the error here is very, very small. It's a good fit. But when we're going way past the data points that we had in terms of where the x-coordinates are, we don't have any x-coordinates up this high, and notice that the errors are getting worse. So this is typically, it's over-predicting a little bit than what the values really should be. Again, it's predicting that y would be 0.18935 when it really should have been 0.18845. So this is one aspect of interpolation, is trying to use it to predict what might happen in the future based on what we know now. But again, you have to be careful. And what's really interesting is that at 10, you would hit a 0 of the polynomial. So the function really should be 0, but the Newton polynomial isn't anywhere near 0. It's 0.00128. So that really illustrates the problems when you're trying to evaluate the polynomial way outside the range of your data. So it's probably best to try to get a data point somehow out here if you really need to have confidence in your interpolating polynomial.